Great. Thank you, Justin, for the introduction, and thank you for inviting me to give this talk. So today I'm going to talk about imaging the Cascadia subduction zone with marine active source seismic data. Specifically, I will be talking about KC21 experiment, the Cascadia seismic imaging experiment that we conducted in the summer of 2021. This is a multi-institutional collaborative project, so I thank my collaborators listed here, and I also want to acknowledge NSF for funding this research. So Cascadia subduction zone stretches over 1,000 kilometers from offshore Vancouver Island in Canada to offshore Northern California. It is where the Juan de Fuca plate subducts beneath the North American plate at a rate of 30 to 45 millimeter per year. It is an unusually quiet subduction zone with very low level of interplate seismicity, as shown on this map. Each dot represents an earthquake, and you see very few dots in this region. However, paleoseismic studies have shown that this margin has hosted great earthquakes, like magnitude 8 to 9 earthquakes during the Holocene, and the latest one occurred in 1700 and caused a tsunami that traveled across the Pacific Ocean and was recorded in Japan. The Japanese people didn't find a local source of the tsunami, so they called the tsunami an orphan tsunami. So now Cascadia subduction zone is at the late stage of its earthquake cycle, so it poses significant earthquake and tsunami hazards to the heavily populated Pacific Northwest. There are some outstanding unknowns about Cascadia megathrust. One is the location and width of the seismogenic zone. As we know, not everywhere along the plate interface can generate earthquakes. And the width and location of seismogenic zone of Cascadia was primarily inferred from thermal modeling, sparse seismic observations, coupling, and also onshore geodetic data. And the models derived from those different approaches have some significant differences. Another important issue is the along strike segmentation in slip behavior. So as shown in this figure from Walton et al. 2021, the current locking status is inferred largely from onshore geodetic data, and the plate, the locking zone is inferred to be wider offshore Washington and is relatively narrow offshore Oregon. And also, there seems to be some persistent segment boundaries during past earthquake ruptures, whether those segmentation reflect geological control or other factors that was not well understood. By the way, can you see my pointer?
Yes, it looks good.
Okay, great, thanks. All right. So active source seismic data are a powerful tool to image the subduction zones at seismogenic depths. In the summer of 2021, we conducted KC21 experiment. We were on board RV lenses, and this was a 41-day cruise. We acquired multi-channel seismic data with a 12 to 15 kilometer long streamer and 66,600 cubic inch airgun arrays of the lenses. And the data were acquired along 18 primary dip lines located 50 to 70 kilometers apart, and also 7 primary strike lines. This program is also complemented by an OBS program and a land program. So the OBSs were deployed on 10 of the dip lines, as shown here, and those velocity structure derived from OBS data will be very important for us to understand the deep structure of the subduction zone. And also over 700 land seismometers were deployed onshore during our experiment to record the shots from the lenses. And in this way, we will have some repass across the shoreline that we can image and also constrain the deeper part of the plate interface. So this is the first modern regional scale seismic survey of the Cascadia subduction zone to constrain the earthquake and tsunami hazards for the Pacific Northwest. Because not everyone, although I cannot see you in the audience, I imagine not everyone is an active source seismologist. So I want to take a few moments to briefly introduce marine active source seismic imaging. basically we use active acoustic wave generated by an active source to obtain high-resolution images of the sediments, oceanic crust, and uppermost mantle, as shown in this example image that is from Nankai subduction zone. You can see the beautiful image of the plate interface and also the faults and sediment strata. So by high resolution, I mean meters to tens of meters. And I want to quickly introduce our source. Here is one of Lance's air gun array. This is the float, and beneath it, those are the air guns. So we have a number of air guns of different sizes hang below the float. And this is a picture of an air gun in real life with my foot as a scale. So the air gun will emit the high pressure air into the water. And this high pressure air bubble will expand and push away the water that will generate this acoustic wave. So after it expands, it will then collapse. So after this peak of the pressure, you will see a decrease of the pressure, and then it will expand again and collapse again. So we will have multiple spikes and trough here until the energy is dissipated within the water. But as a source, you do not want your source to have multiple spikes. In order to address this, we use multiple air guns. So by using multiple air guns and of different volume, the air bubbles can expand and collapse at different periods. So we can align their first spike together, like here, and then let the second spikes cancel out one another like this. So by adding all these up, we can have a sharp spike at the onset of the time, and then a low energy for the rest of the time. So in this way, we can have a really nice source. And for the Casey experiment, we used the full volume of the Lance's air gun array, this 6,600 cubic inches. And for receivers, our receiver is different from many of you are familiar with. So this is a seismometer that many of you use for your research, but this is our receiver. We use the hydrophones located along those yellow cables. The hydrophones are grouped into sections, usually at 6.25 meter or 12.5 meter spacing. And so each hydrophone group is called a channel. So that is where the multi-channel seismic, this is where the channel from. And the streamer can be up to 15 kilometers long with thousands of hydrophones. So it might, for the Casey cruise, we used 12 to 15 kilometer long streamer. And it might be difficult to picture in your mind how long 12 to 15 kilometer is. I was trying to think of a reference that can give you some idea. So I think, oh, maybe I can use Manhattan in New York City. So here is the Statue of Liberty, Empire State Building, Central Park, and the Metropolitan Museum of Art. So this is Manhattan Island. Okay, if you start at the southern tip of Manhattan, 12 kilometers. With 12 kilometers, you will reach the northern end of Central Park. And with 15 kilometers, you will actually end up in Bronx. So now you have an idea. So 12 to 15 kilometers is about the length of Manhattan Island. So think about during our experiment, we tow a long cable, the similar length of Manhattan behind our ship. I think that is pretty cool. So for seismic record, so as seismologists, we plot travel time versus distance. This is a typical seismic record many earthquake seismologists use. And we have similar plots, but just we flip and also rotate our plot. So the vertical axis is two-way travel time increases downward, and then this is our offset. So you can see like this is an example of a shot from Casey Cruise and a figure made by Brian Boston. So this is direct arrival, and the wave travel directly from the air gun source to the streamer. And here is seafloor reflection, and those layers are reflections from sediment layers, and this is the reflection from top of the ocean crust. And we also have some refractions. Here are the refractions travel through the top of the upper oceanic crust. And we also have some multiples. So those are the waves that bounced twice between the seafloor and sea level. So because we have so many traces, and this is a shot gather, and then in our processing, we will sort them into CMP gathers. So for each CMP gathers, they sample one subsurface point with many traces, and those traces with different offset. And then we can use correct velocity. We can correct them and bring them to the same travel time, and then stack them to increase the signal to noise ratio. I mentioned this because I want to let you know the advantages of long offset multi-channel seismic data. And this, with so many channels, we can greatly improve our signal to noise ratio through stacking hundreds or even thousands of traces. And also, the move out of those reflections and these refraction arrivals can give us important velocity information that we can use for our imaging. For the Casey cruise, after the data acquisition, we worked with an industry partner, Ion Geophysical, to process the data. So here is our processing flow, and I will not go into details, but just let you know we removed noise, multiples, and then I did a bunch of the signature, and then we built our velocity model. Then we processed data up to pre-stack depth migration. So here I'm showing you an example. This is our PD09 line located offshore the mouth of Columbia River. So this is in one of the data gaps from previous active source seismic data coverage. So you can see this bright reflection is the top of the oceanic crust and is dipping landward. So this is ocean, this part is land. And then this bright reflection is oceanic moho, is the base of the oceanic crust, is also following the shape of the top of oceanic crust and dipping landward. And this section is the incoming sediment section. They are scraped off and deformed by faulting and folding. You can see those deformed sedimentary layers. So this forms the outer wedge. And then for the inner wedge, it shows like incoherent reflections, but above it, you can see this shelf basin and the basin overlying the upper slope here. So for today's talk, I will be talking about 4 studies. First is about plate interface geometry, and the second and third is about the outer wedge. And then lastly, I will be talking about the mass transport deposit that we observed offshore Southern Oregon. So of these studies, the study 2, 3, 4 are led by my graduate students and myself. So the first study, the plate interface geometry, this study is led by Suzanne Carbot at Lamont Doherty Earth Observatory. We have submitted this paper to Science Advances, and currently it is in revision. So as I mentioned, when I showed you the example pre-stack depth migration image, we can, from the Casey data, we can image the plate interface pretty well. For most of our lines, we can see the top of the oceanic crust and some lines oceanic moho to pretty close to the end of our line and close to the coast. So for these examples, so A is PD07 offshore Washington, and this is the other line is offshore Oregon. You can see on both of them here, the yellow line is the top of the oceanic crust, and the blue line shows marks the oceanic moho. And here is the outer wedge deformed by thrusting. And you probably have already seen the difference of the dip of the plates. Here on this line, the plate is shallowly dipping, and for this Oregon line, the dip, it's steeply dipping. And this is more obvious when we look at a long strike line as shown here. So on this line is 10 times vertical exaggerated. So it's just to squeeze it to fit into the page. again, the yellow line is the top of the oceanic crust, and the blue line is the oceanic moho. You can really see the up and down here. So the left-hand side is in the south, and the right-hand side is in the north. So we can see like in the center part between 44 and 47, the plate is pretty deep. And there you can see a fault here. There's a fault where there is a few kilometers offset, the plate step up. And then in the south, the plate also is shallower. So we interpret the top of the oceanic crust and for all of our profiles and make a map like this. This map is trying to capture the long wavelength variation of the plate interface of the top of the oceanic crust geometry. And we find it is pretty well correlated with the heterogeneous upper plate structure above. So let me explain from north to south. So in the northernmost part, we see the plate is dipping steeply offshore Vancouver, northern Vancouver Island. And this part is also influenced by the Nootka Fault Zone. And offshore southern Vancouver Island and Washington between 48.25 and 47, this part is the flattest part as shown on these profiles. And this is also where the bend of the subduction zone is. The dip of the plate near the deformation front is only 2 degrees. And then like as we go south between 47 and 44.5, you can see a gradual increase of plate dip from north to south. And also the steeper part of the plate is closer to the deformation front as we go south. And then like for the southernmost part where we're in Gorda plate, then the plate dip becomes shallower again. So if we look at the upper plate terrains here, we can see there where the plate is the deepest is where this Celeste terrain is. So this Celeste Crescent Formation is an accreted oceanic igneous rock and volcanic classic rocks that of Paleocene and Eocene age. And then like east of it, there is this Franciscan terrain that was transported from south, and now they're adjacent to the Celeste terrain. For this green color is the Olympic Formation that is an older accretionary wedge that is of Miocene or older sedimentary rock. And then the purple color is the youngest, the Pliocene-Pleistocene wedge as shown here. So what we see is where the plate is deepest is where this Celeste terrain and the Franciscan terrain is. So we think when the Fuca plate is fragmented within the seismogenic zone as a young plate bend beneath this heterogeneous upper plate. And then this results in the segmentation that correlate with this paleo rupture segments. And another thing I want to point out is, although the plate interface is at the top of the oceanic crust for most parts, there are 3 places that it deviates from the top of the oceanic crust, as shown in these lines. So offshore southern Vancouver Island and Washington, we observe a shallow décollement above the top of the oceanic crust. And the formation of these, we think, are related to the faulting of the top of the faulting of the oceanic crust. And those formation of the sediment décollement help to smooth the plate interface. So when it's ruptured, it's more energy efficiently when it ruptures. And for the southern part, offshore southern Oregon, we see there is a shallow décollement near the deformation front, but then it steps down when it meets this static backstop at Franciscan terrain here. So Another thing I want to mention is a comparison of the new plate boundary model versus the widely used SLAP 2.0 model. So here is the SLAP 2.0 minus the KC21. So when the color, the red color shows the new model is shallower than the old model, and the blue color is showing the new model is deeper than the SLAP 2.0 model. We can see that near the deformation front for Washington and Northern Oregon, the two models are pretty consistent. But for the deeper part of the Oregon, Vancouver Island, and the shallow part of Oregon, the new model is shallower, whereas for the deeper part offshore Oregon, the new model is deeper. Okay, now let's move to outer wedge. So for outer wedge, this study is led by my graduate student Danqi Jia. Danqi has been looking at the structural variation of the outer wedge. So I will show you some examples from north to south. So here is a line offshore Vancouver Island, our PD02 line. You can see this is the outer wedge. It's about 20 kilometers wide. And within this, these faults are landward virgin faults that reach the top of the oceanic crust, meaning the entire sediment section is accreted. So I want to mention, like, around this region, the outer wedge structure is highly variable, although we see the landward virgin faults here, but on nearby lines, we also see seaward virgin faults near the frontal thrust. So offshore Washington, we see this outer wedge now is a lot wider. So it's about 50 kilometers wide at this particular location. And again, we see landward virgin faults reaching the top of the oceanic crust. So full sediment accretion for the outer wedge part. And also, except for the frontal wedge, we see the older thrust wedge are covered by recent sediments, as shown in this here, those fat sediments. And then when we get to offshore Oregon, we see different picture. Here we do not see the well image layered structure coherent reflection here. Instead, we see, although we still see reflections, it's not like those nice layer structure as we saw in the north. So here we see some deeping structure that we interpret as seaward virgin faults. And those faults, they seem to show into a décollement. As I go back and forth, this reflection. And so instead of fully accretion, here only the upper part of the sediments is accreted, and the deeper part is subducting. And then the underthrust sediments, this décollement steps down to merge to the top of the oceanic crust. So the sediments do not make too deep into the subduction zone. And then when we get to the southernmost line, as shown here, we again start to see this layered structure that deform the sediments. Now the faulting pattern is more complex. So instead of dominantly landward virgin or seaward virgin, we see both virgins. And the sediment outer wedge is about like less than 20 kilometers wide. So this along strike variation of structural deformation styles have been recognized along the Cascadia margin for many years. And the major advance for KC data is one, we have filled some critical data gaps. So for example, for offshore Southern Oregon, now we have the deep image to see this part of the margin. And second is now we have depth image of this data. So we can determine those fault geometries accurately and do quantitative analysis. And this is what Danqi does. So previous images are mostly in time. So Danqi interpreted all the faults in the outer wedge that she can interpret. And now in this figure, she plot the major faults, the faults that connects to the plate interface. So the orange color is a major landward virgin faults, and the blue color is a major seaward virgin faults. And you can see that they are of two population In general, the landward verging faults are steeper than the seaward verging faults. And from the histogram, they also have smaller variation than the seaward verging faults. So Dante also examined the along strike variation of the fault dip as shown in this figure. So this is north, this is south. The Vancouver Island, Washington, and Oregon, each dot represents an average dip of all the major landward or seaward verging faults along this particular dip line. So you can see the average dip of the landward verging faults is pretty stable. It's between like 40, 45, 35. It does not show much variation along strike, but the major seaward verging faults shows larger variation along strike. And Dante also looked at the down dip direction. So here is an example of a line from the landward verging zone, PD06. You can see all those are landward verging faults. And here is an example of PD13 from the seaward verging zone. So each dot here is a dip of a major fault. You can see this is a distance from deformation front landward. So from deformation front landward, the landward verging faults has pretty stable dip. It's between like 30, 40, but there is an increase trend for seaward verging faults from gently dipping near the deformation front to increase the fault dip increases with distance from the deformation front. So it looks like the thrust sheets are stacked and then rotated while they are accreted. So there are two different accretion style for the landward verging faults and seaward vergings. So we think this reflects the different strengths of the sediment material that's forming this landward verging zone and seaward verging zone. And that leads to the third study led by myself. So besides looking at the images, we can also look at the seismic velocities. So the seismic velocity contains information about the physical properties of the rocks. For sedimentary rocks, porosity is an important factor to control the velocity. So here I'm defining a reference velocity from the incoming sediment section that represents the normal consolidation scenario for the change of the velocity. So for normal consolidation, it's like in the sedimentary basin, the sediments are compacted and then the porosity reduced, so velocity increase. And with no the compression from other directions. So I then subtract this reference velocity from our velocity profile, then this is the residual velocity. So the residual velocity, the blue color represents the velocity is higher than the reference velocity, and the red color represents the velocity is slower than the reference velocity. So here there is a big assumption is the material we're looking at is the same lithology. This probably is true if you look at the sediments from the incoming plate section versus outer wedge, because it's the same material created, but it may not be true when we go from inner wedge to outer wedge, because it could be like different material. So the residual velocity can reflect the anomalies in consolidation states, can also reflect difference in lithology or stress state. So in this exercise, we first subtract this reference velocity to get a residual VP, and then we examine the reason that caused this residual velocity. Okay, so now let me show you from north to south the lines we have seen the images. Here are the residual velocity of these lines. So after subtracting this reference velocity, we see here this a line offshore Vancouver Island. This blue zone is higher velocity than the reference velocity. and it corresponds pretty well with where we see those active deformation on the outer wedge. And then when we go to the PD08 offshore Washington, we can see now the blue zone is wider. And this pockets of neutral velocity actually corresponds with those newly deposited sediments on top of those thrust ridges. And then inward, this blue transition into this red color. So this part is slower than the reference velocity. And then when we get to offshore Oregon, we can see this here. First of all, this outer wedge is pretty narrow, and the entire outer wedge is of this red color, so it's slower than the reference velocity. So when we get to the southernmost line, where we start to see those layer structures deformed by folding and faulting again, we also have our blue zone back. We now see a relatively narrow blue zone, and then transition to this red zone. So we want to look at the spatial extent of the wedge with positive residual velocity. So what we do is we define this transition from positive residual velocity to negative residual velocity, and then put it on the map. So this is the blue zone here now is on the map. We can see that the part of the wedge with positive residual velocity is the widest offshore Washington and is narrowest offshore Central and Southern Oregon. So if we look at seismic image and see there is this also a change in reflection character. So here, like in this part, we can see the layer structures deformed by faulting and folding, pretty well coherent reflection. And then like when we get landward, it becomes quite incoherent. So this transition from coherent reflection to incoherent reflection, we can also define a transition and put it on the map. And turns out, so this yellow line here is the transition in seismic character. And so this boundary correlates pretty well with the transition from high residual velocity, positive residual velocity to negative residual velocity. And so this boundary like is used to the transition in seismic reflection character is used to define the Pliocene-Pleistocene wedge. So by Lucas et al., and this paper is in preparation. So these two lines of evidence fit pretty well. And then there is a third line of evidence from tectonic geomorphology that is a study by Watt and Brothers. So they looked at the bathymetry and also some shallow seismic data and defined the dynamic backstop that is at the boundary of this Pliocene-Pleistocene wedge. So that is shown in this green line here. So this is the change in the slope of the wedge also gives information about this transition from inner to outer wedge. And this is a line from their boundary, and it's also this line that's separating the purple part and the green Olympic formation, the older wedge. So this line also fits the transition in velocity pretty well. So now like both the velocity and the seismic reflection character and seafloor bathymetry all support, like we put this boundary here. So we can now see this high velocity is because this Pliocene-Pleistocene wedge is likely over-consolidated due to this compression, because from the reference velocity defined on the incoming sediments is with horizontal compression in the outer wedge, the porosity is reduced and now the velocity has increased. And here we satisfy the assumption that this is of the same material, the same lithology. But then this inner wedge, the red colored lower velocity inner wedge, probably is it's shown as a negative residual velocity, probably is because of the lithology difference between the outer wedge material and inner wedge material. So the inner wedge material is of older Miocene or older accreted wedge, and it also has this broken and melange formation So there, in this part, there is also mud diappear and overpressure, evidence for overpressure from industry drilling holes. So maybe overpressure also played a role in reducing the velocity in the inner wedge. So how about this part of the offshore southern Oregon? This part does not seem to have a high velocity wedge. Why it is missing? So we first consider, is it because of the reduced sediment input? As some of you know, the recent sedimentation of Cascadia Subduction Zone is dominated by two major submarine fans, the Nitiad fan in the north and the Astoria fan in the south. And the spatial extent of these fans correlate really well with this widest part of the Pliocene-Pleistocene wedge. So it is possible that the reduced sediments is the major reason that we do not have this wedge offshore southern and central southern Oregon. But when we looked at the incoming sediment thickness at the deformation front, we see that it is not significantly thinner than the north. So, okay, so this point is thinner, but everywhere except for the southernmost line is over 2 kilometers thick near the deformation front. And the incoming sediment thickness in this region, although it's less than near the Astoria fan, but is similar to between 46 and 47 in this part. So if there any other reasons that can cause this change, or could there was a small accretional wedge, then a small Pliocene-Pleistocene accretional wedge that is destroyed by something, maybe landslides, and that leads to the fourth study here. So this study is led by my graduate student, Charles Bevendreyer. And indeed, we have imaged paleo-landslide deposits offshore southern Oregon. As shown in this map, you can see like those are the landslide deposit or landslide complex. They extend over 50 kilometers from the seaward of the deformation front, and there are multiple events of them. If you take a closer look, you will see like some part they have the thrust and fold structure, some part is more chaotic, and some part is like angular blocks. So those landslide deposits, we're not the first people that image those landslide deposits. And it has been imaged before with older seismic data and studied with bathymetry data. But the improvement from Casey data is like we now have, with a deep penetrating source, we can image the entire sediment column well. So we can really image the deep structure very well. And also we have this pre-stack depth migration that can accurately define the geometry. And also our lines extend pretty far away seaward of the deformation front, so we can capture the full extent of those landslide deposits. So Charles has mapped all of these landslide deposits and there are 10 of them as shown in different color. So these are we imaged them on 5 of our dip lines as shown here from PD14 to PD18, and also on an along strike line as shown here. These are the events. And Charles also put them on the map view as shown here. So they're only imaged between 42.4 degree to 44.3 degree. So the landslide deposits of this scale are not observed anywhere else along the Cascadia margin. So they are really massive events, and with the largest covered open area of over 5,000 square kilometers. And Charles also conducted stratigraphic analysis in combination with biostratigraphic constraints from ODP size 168 in the north. And the age estimate suggests these slides occurred within the past 1 million years. So this time fits with like the rapid sedimentation of related to the Astoria fan and Nitiad fan. So it is possible that this massive landslides just destroy the accretional wedge, and so we do not see those well-preserved layer structure as we saw from north and south. So a quick summary of the new observations from the KC21 data. Now I put them on the map view. So offshore Vancouver Island and Washington and Northern Oregon, we see like a strong and wide outer wedge with little sediment under thrust. In offshore Central Oregon and Central and Southern Oregon, we see a weak and narrow outer wedge with thick sediment under thrust beneath the outer wedge, and also massive landslide, paleo-landslide deposits. So the thrust fault distribution and geometry in the outer wedge in Dante's study reflects the variation in sediment strength. So then, what are the implications for plate interface locking status? So here is a figure of the viscoelastic locking model from Lee et al. 2018. And we can see that between 42.5 and 44.5, the model shows there's less locking in this zone. So here is also where we see this weak outer wedge and thick underthrust sediments. So we think the pore water contained in the underthrust sediments and also this relatively weak wedge, supposedly more porous wedge, could provide fluid and maybe elevate pore fluid pressure along the plate interface and contributing to partial creeping. And then for tsunami genesis, we see this variation in the wedge properties from north to south. And here is a modeling study by Aldrich et al. 2022. And from their study, they found the stronger sediments cause high fault slip, as the trench is more localized seafloor uplift near the trench. But for weaker sediment, it will be widespread plastic deformation of the megathrust. So it's more distributed seafloor uplift over the wedge. So that the strong wedge scenario will correspond to where we see from Northern Oregon to Washington, and the weaker sediment is what we find offshore Southern Oregon. So, so here is a summary of our study so far, and some of the work is still ongoing, and I welcome your feedback. And here is a summary of observation that I just mentioned, and here are the implications. I will just put it here, but I want to emphasize that we think the variations in the shallow megathrust properties and outer wedge strengths should be considered in the assessment of earthquake and tsunami hazard of the Cascadia subduction zone. That's all for my talk, and thanks again for your attention.
Excellent. Thank you so much, Dr. Han. What an interesting presentation and fabulous new data set for people to dig into. This is great. I wanted to remind our audience that if you have a question for today's speaker, please go ahead. You can start sending those in via the Q&A box on your Zoom control bar there. We did have one early question come in from Heidi Houston about some of the offsets that you observed right at the beginning of your presentation, the offsets in the oceanic moho. And I know you mentioned one, I think there was a faulting, or a fault maybe that had caused a jump in the depth of the oceanic moho, but maybe you could just say a little bit about the variation there and maybe the impacts of the faulting on that.
Yeah. Is it like so all those offset in the oceanic moho? I'm not sure like which slide. We certainly see offset of the oceanic moho. So
yeah,
do you mean
I think
here?
so. Yes.
Yeah. So for here, like on this line, we see the top of the crust, and so the moho reflection is not as continuous and bright as the top of the ocean crust reflection, but I was referring to PT09 on the left.
Yeah.
Oh, okay. So here. Okay. Yeah, I think that there are some minor ups and downs of the moho reflection, but I think that on this line it is mostly continuous. We do see offset of moho on some of the lines, and at some places we see they're correlating with the offset at the basement, so we think they are real.
Okay. We have a question here from Kelsey that says, wonderful talk. Do you think that the lithology of the backstop, so either the Silesia or the Franciscan versus Olympic complex, plays any role in what you see in the outer wedge?
Yes, I think so. It looks like the lithology is playing an important role. Let's see. So if we look at this figure, so for the backstop here, those Franciscan formation, it is pretty close to the deformation front, and here like the Olympic formation and this hard rock formation is farther away. The Celeste terrain is farther away, and this relatively soft material is in between this hard rock. So I think it probably plays a role in how far a rigid body is close to your deformation front. It does have an impact on the structure of the outer wedge.
Okay, got a two-part question here from Jaivin. Thanks you for the presentation, and says, first, does the tectonic processes like faulting in the Juan de Fuca plate influence the subduction process? And then also, secondly, here in the new data, the basement and the oceanic moho seems to be negative polarity. How do you explain this?
Okay, so the first one, does the tectonic processes faulting in the Juan de Fuca plate influence the subduction process? Yes, we do think there is a good correlation between, as we've shown in this first study, the faulting, like as we saw, for example, here this fault in the oceanic plate, and then it probably we also see a shallower décollement on top of it. So this décollement is kind of smooth this offset in the oceanic crust. So this ups and downs and faulting and indeed like impacts the coupling like along strike, and also like it correlates pretty well with the paleo-rupture segmentation as we've seen from other studies. And here in the new data, the basement and oceanic moho seems to be negative polarity. I do not think so. I think they are positive polarity because yeah, I'm seeing if we can see a zoom in the view for that. Sorry, it's like I do not have a zoom in for the seafloor, but if we have an image, you will see like the basement and moho reflection polarity is consistent with seafloor reflection.
There was a kind of an addendum here to this asking about whether the data will be made public. Are they currently publicly available, or do you know when they will be publicly available?
So the PSDM images are publicly available in the, I believe it's in the Marine Geoscience Data Center.
Okay.
But the studies we're showing here, the first one is currently in revision and the other ones are not published yet.
Okay. Excellent. So we've got several other questions have come in here. First one from Edwin says, I'm interested in whether you looked in detail at the shelf and whether you see any active splay faulting there too.
Active splay fault in the shelf. So Maddie Lucas, student working with Harold Tobin at the University of Washington, has been studying the transition from outer wedge to inner wedge and examining whether there are splay faults in this transition zone. And I think her conclusion is there is not a thorough-going splay faults along the entire margin, but in some parts of the margin there seems to be active splay faults. Believe it's near our PD10. So further within the shelf, I do not think there are splay faults within the shelf. It's mainly in the transition between the outer wedge and the inner wedge.
Great. Another question here, it says, can we use the dip of these outer wedge faults to infer the frictional strength of the outer wedge sediments? And if so, are the inferred frictional strengths consistent with the strongness versus weakness inferred from the consolidation state?
Yeah, this is a great question. We're currently doing that by using the angles of the faults, and also by making use of the faults in the protosthrust. We're currently calculating the inferred strengths of the sediments and compare it with the result we have from the velocity data. And yeah, we will have some results soon, but not yet.
Stay tuned.
Yeah.
Okay. Next question here asks, did you estimate the proportion of sediments that are subducted past the inner and outer wedge that can affect the deeper megathrust?
Right. The proportion of the sediments that are subducted past the inner and outer wedge. Yeah, we do see a deeper sediment décollement above the top of the oceanic crust offshore Washington and southern Vancouver Island. So yeah, so for that, like there is indeed like evidence of sediments being carried down and then later up underplated. Say the uplift of Olympic Peninsula is evidence for that. Yeah, I think like by having more sediments down deep, and also another thing I want to mention is, so the sediment subduction probably is a time varying thing. So currently we're seeing full accretion near the deformation front, but that does not mean it is the case in the past. So like it is possible that what we are seeing from the difference between the near deformation front and deeper part reflects the time varying process. But I do think the deeper subducted sediments can affect deeper megathrust. Potentially it can bring more fluid and increase the pore fluid pressure along the megathrust.
Okay, just a few questions left here. This one from an anonymous attendee asking if you'd care to speculate about how your observations and variations along strike, how they might impact how common or uncommon a full-length megathrust earthquake would be on the subduction zone.
This is a hard one. I do not know. I do not know. How can we know? I mean, what we observe are those structural and physical property. We do see a lot of variations along strike, and some of these might contribute to be persistent segment boundaries. But for any specific earthquake, it could also rupture over those boundaries. Yeah, I do not, sorry, I do not have
That's okay.
a better answer to this.
That's all right. Okay, maybe our final question here then asks if you could you speculate on the role buried seamounts might be playing or not in contributing to the residual velocities that you observe?
Those buried seamounts. So in the current study, like what we have interpreted the top of the crust, and the part of the section I apply this residual velocity is only for the upper plate, as the accreted sediments. So I do not think it will impact unless we interpret the top of the crust. We made some mistake in actually interpret the plate interface below various seamounts. So I do not think that have an impact. But if there are some seamount that older seamount that now are created and in the wedge, then it might be shown as a positive velocity anomaly. Yeah.